In the last video, we talked about the issues with overfitting our model to our data. And one way we can address and try to prevent overfitting is through a process called cross-validation. So this is where we left off last time, and we really had two main themes that I left you with. The first was this idea that the model's not encountering all of the data. There's this unseen data set, unseen data in the real world that you want the model to be able to predict well with. And then the second idea is that a model's complexity, which we're going to define as its number of features, will influence if it's under or overfitting. And again, our goal is to find this sweet spot. So in the next few videos, we're going to address this. And in particular, today, we're looking at what's called cross-validation. After this, after we finish the cross-validation videos, we will introduce a second way that we can help prevent overfitting, which is called regularization. And these two are often used together. So here was where we left off last time about having too complex of a model. And so one way that we can quantify this, be able to say, oh, this is not doing great, is introduce what's called a test set. So this is a portion of your data set you set aside for testing purposes. So here's our full data set. And imagine then we split it up into a portion for training and a portion for testing. And we leave the testing data set. We don't use it to fit our parameters. We only use it once after we have fine-tuned our model and decided, okay, here's our final version. Then we use it to see, okay, what's our RMSE? What do our residuals look like? This is like our final answer. And there's a way to quickly do this train test split. The documentation I have linked here, we're going to see in Python. It does this nicely for you. You can also do it manually. But there's a downside to doing this. Because if you're dissatisfied with the test set performance, you can't go back and change the model in this framework, because then you'll actually be factoring in information from the test set to design the model. And we really want the test set to represent performance on unseen data, because that's what's going to happen in reality. When you send your model out and it's used on new data or unseen data, you don't then get to come back and reiterate or continue to rework on the model on that data. I mean, and if you did, right, if that's part of your process, it's fine, but then you don't consider that a real metric of how your model's doing on unseen data. So what we're going to do in our process is introduce what's called a validation set. And that's a portion of your training set we set aside. Think of it as like we're going to split the training set into a mini training set and then a validation set. So here's a visual of where we left off, and now I'm going to take my training set, split it up into a mini training set and a validation set. And then I can use these two to iterate back and forth. I can do multiple rounds of the modeling process here. When I do this method, this is frequently referred to as the cross-validation holdout method. So you train the model on this training set, meaning I fit my theta parameters just using this data. And then I go calculate my RMSE and my residuals or my adjusted R squared using this, right? The validation set, which was not used to train. And so I'll get a fair, unbiased assessment of how this model's doing by using that validation set. And then I can say, okay, well, if this is not what I wanted, then I can go back and adjust. Maybe I add more features. Maybe I do some types of transformations and see how the model does and then test it again on the validation set. This is completely reasonable practice because I'm not touching the test set in this process at all. The test set's not being used to iterate on the model. Once you come to some satisfactory version of your model in this process of training, validating, then you can assess the final performance once on the test set. So that whole process is called the holdout method. And let's go see this in practice with our vehicles data set. So we're still in the cross-val notebook, which is in the modeling/linear regression folders. And I'm just going to remind you what we saw in our last video with the complexity and overfitting is we were trying to fit this vehicle data using horsepower to predict miles per gallon, and we were using higher and higher degrees of horsepower polynomials. And we were finding, oh, the higher we went, my mean squared error was basically still decreasing. It's kind of bouncing around right around here. So let's use the holdout method of cross-validation to determine if we're actually overfitting, right? And maybe we should stop at degree 4 or degree 2. We'll be able to see that because our validation mean squared error is going to start to increase. So jump down here to the cross-validation section. All right, and so just to let us play around with some different powers, I'm actually just going to add up to the 8th degree polynomial to our data set. And now we're going to split the data. So the first way we can do this is manually using pandas operations. You can imagine here, I just want to shuffle the data here. I'm putting a random seed so that we all get the same shuffling when we're going through this, but that's not necessary. So here you can see I've randomly shuffled the data, and then I can say, all right, now I want to select a certain percentage for my training versus my testing. Okay, so it's common practice to use anywhere between 75 and 90% of your data for training, and then the rest for testing. I'm just going to do 80% here. So now that tells me that 80%, the split point, is at 313, like the 313th data point here. So I can now put my training versus my testing and show you, all right, I made the training be the first 80% and the testing is the last 20%, and we can see they add up to be the whole data set. Now, in practice, scikit-learn has you covered here. You don't have to do this manually. There is a function called train test split that will do exactly this. And so you give it the X design matrix, your Y predictor vector, your whatever test size you want, so 20% is what we were using. And I'm putting a random state just so we get the same split, but this is not necessary. Same split as one another here. And then I'm putting shuffle true. So I want it to randomly shuffle the data set first before it splits it up. And I want you to think about why that's important. If I want my test set to be representative of, the random thing I might actually encounter out in the real world, then I want to make sure I've randomly shuffled my data before I split it into training and test to try to prevent any type of non-random patterns from showing up in the test set and in the training set. Okay, so here I now have the training set and the test set, and I go to fit the model. Okay, so I haven't done a validation set yet. We're doing the first step here. I go to fit the model, and then I say, oh, my training error is 18, and your test error is 20. These are mean squared error that I'm doing here. It is typically the case that your test error is higher than your training error. Not always, but it's not unusual because your model has not seen any of the test data, right? When I was fitting it, we were just using the training data. So it's not unusual that that will be lower. And if you are saying, wait a minute, I thought we were only supposed to use the test data once, you're correct. If this is what I had done, I wouldn't be able to make it any further iterations. If I use my test data set, I'm done. So let's introduce our validation set first. We can fine-tune our model. And then at the end, once we've decided what version of the model we'd like, we can use the test. And by what version we like, right now, I just added in up to 8th degree of horsepower, and that's what the model fit. It fit using all of these. But maybe I want it to stop after 5th power, or 7th power. That's what we're going to play around with using our validation set. That's a process, a way of helping us do model selection. All right, so now let's do another split. So I'm calling this train test split again, but I'm putting my train in here, right? So that I can get my mini train and my validation out. And I'm keeping it, again, 20%. So really that's going to be now my validation set is 63 points. My mini training is 250. And then the original training, the whole thing altogether was 313. So now what you can see is I'm going to practice fitting several models of increasing complexity. I'm going to look at models of order 2, 3, and 4, fit them, and see how their validation mean squared error compare. Right? So, okay, this is positive. It's decreasing. I have 12.4 here. It's going down, 12.196. Down slightly, 12.193. So it's slightly better, maybe not a huge improvement. Let's repeat this process, though, looking over more than just 4 degrees. So again here, I have some code that's just to make this a quicker and more concise thing to run. It's involving sklearn pipeline function and polynomial features, which are out of the scope. It's just a quick way so that I can plot this, our best fit up to power 18, just so we can see what's happening. Okay. And so I'm going to point out here that all I'm doing is plotting my validation mean squared error. And like we'd expect, at some point I start to overfit. Oops. And that's really what this is capturing. As soon as this starts to increase again, I'm starting to overfit. And so I really just want to pick a model complexity here where I have the smallest mean squared error. And so if I do this here, we can see here's all of my degree and the mean squared error, and I can see it's decreasing, oh, sorry, I don't know what happened there. It's decreasing. Something really wants to print right now. Okay, it's decreasing till degree 8, and then it starts to increase. So if I were just using this, I could say, all right, maybe we'd stop at degree 8. I'm going to come back to the fact here that if you're wondering, like, there's a slight improvement from degree 7 to degree 8. I mean, really, you could argue you want to stop as soon as degree 2 or 3, because we're really not getting that much improvement here, and adding more complexity risks that we're just increasing our model variance. So it's not that you absolutely have to have the minimum. You could make an argument here for something closer to 2 or 3. And we're going to talk about that actually in the next video when we take into account this really depended on that 80-20 split that we did for our validation versus our mini training set. And what if, by random chance, our validation data set's not really that representative? Do we really want to put all our eggs in that basket and really worry about these tiny, tiny differences here? Or should we try to check for something a little bit more general? So that's what we'll talk about in the next video with k-fold cross-validation. But at this point, without doing that, you could stop from this method and say, all right, I'm going to choose degree 8. That's going to be my final model. That's the one that I like. And then you can train. We use the validation set to help us pick that power, the degree 8. That's called a hyperparameter. Once you've decided that, then you can go back to use the entire training set, so both the mini and the validation set, to fit our final model. Because I want to use as much data information as I can. Let's see. We're going up to degree 8. Yeah, so what this is doing is just adding up to degree 8, and then we're going to fit it right here on the entire training, mini training and validation set. And then we'll do our test once at the very end, right, to see how low we go. Okay, so at the very end here, I can now see this test mean squared error is 20, right? And again, I would also want to look at residuals and perhaps adjust it R squared. For the purposes of this video, I just wanted you to see this process of holding out, using it to fine-tune a hyperparameter, and then making your final choice on the model. So I'm not going through all the modeling diagnostics and evaluations in this just for the sake of time. But let's pop back to the slides to finish this off to make some conclusions. So we saw this, and I'm going to now relate that back to the schematic that we had been using, relating model complexity to training error and variance. What I'm adding on here now is our validation error, right? And so this is like an idealized curve. This gold one here is kind of idealizing what the general trend we saw here. And we basically pick a point at which our validation error is low and it hasn't started to increase. So what this is telling us is that typically as your model complexity increases, your training mean squared error will decrease, but the variance increases. And again, we haven't measured the variance in this video. The way I really shown it to you is by looking at this validation error, right? Because that's going to kind of mimic the variance. But there is a mathematical definition of this, which we are going to get to in our future video. It just involves a little bit more theory, and it's more along the inferential side of this modeling process. So for now, I like you just to have this visual in your head. And so our validation error is really what we're using to help us figure out what level of model complexity to stop with. And so our goal is going to be try to choose this model complexity that minimizes validation error. One way we're doing that is by checking our validation error through this holdout process. And we're going to learn another way to do this using what's called regularization in a future video. So let me just summarize what we've done so far about cross-validation. So far, we've looked at the first method for it, which is typically called either the holdout method, or sometimes you'll hear it called simple cross-validation. And that's what we just did. We broke the data into a mini training, a validation, and a test set. And we used the mini training to fit the parameters for the model. We used the validation set to score the model. And then once we had come to an agreement of what we wanted to choose for our final model, then we used the test set once. However, I did mention that we could be a little bit worried that maybe, we have all our eggs in this basket of this particular validation set, and we're fine-tuning and iterating on the modeling process based on this particular validation set. And what if we just happen to, by chance, got a pretty unrepresentative validation set? That's what we're going to take into account in the next video. There's a process that tries to capture that possible variance that you might get from your random selection of a validation set, and just kind of smooth out that possible randomness in a process called k-fold cross-validation.